Well, first of all, thanks everyone for being here. It is very rewarding and refreshing to see so much participation. I see many students. I see many members of the staff, many members of the faculty. I noticed that the department chair also joined. So plus we have several alumni. So this is outstanding. Thanks. You're really making my day. So this research showcase is all about the students. We want to celebrate the great research that our graduate students are performing every day in our department. And so I'm not going to talk for too long. I want them to be at the center of this event. I just want to say a few words to explain why we really wanted to kickstart this event. And also I want to explain a little bit how this is going to work. So first of all, this is an event that was strongly supported by the department. We realized that we were in lack of opportunities to celebrate the great research of our students and also to share ideas, get to learn what we are doing in the department, and so we thought that this would be the excellent mean to achieve that. So the department tasked a team of professors and students to organize this. So I want to acknowledge all the contributions from my dream team. So Professor Meram Esbai, Justin Little, Carl Nolan, Dana Dabiri, and our rising star student, Lando Bevier. I also want to acknowledge all the help from Amy Sprague, without whom this would not be possible. She, as you can see from the graphics, she really helped and, made this a reality. So thanks for that. Without further ado, let me go to the schedule. So this is how this is going to work. So we're going to start soon with lightning pitches. The students are going to present for 2 minutes each, and they're going to show you why their research is awesome. So that's the goal. The goal is to provide you a brief idea of what they're working on, why their research is impactful, and hopefully they're going to get you curious to visit their posters in the following session. The poster session is going to start at 6 and is going to last until 6:55. So the way this is going to work is that there's going to be several breakout rooms. Each student is going to be assigned to a different breakout room, and you will be free to move from one breakout room to the other. So try to visit as many posters as possible. Try to have fun. This is the goal of this event. If you want to know the number of the breakout room, this is going to be announced during the pitches. So Landon is going to call the student name and is also going to announce the breakout room number. In case you're not able to take notes, well, at the end of the pitches, Amy is going to post a link that is going to have a list of all the titles of the presentation, student name, and the room number. So don't you worry. As you will see later today, we want to give prizes to our students. And so at 6:55, don't go away. Our chair is going to announce awards to the students as selected by a team of judges. So as I mentioned, there's going to be prizes. We're going to have a team of experts assigning awards to the best combination of pitches and posters. I know you want to know who the judges are, but I'm not gonna reveal that. You're gonna wait until later because we want to spice things up a little bit. So first prize is gonna be $600. Second prize $300. Third prize $200. And I'm very excited to tell you that everyone in the audience is gonna have a say. So we also have a People's Choice vote, which is gonna be about $300. So if you want to express your opinion, if you want to vote, please use the link that you see in this slide. Amy is going to paste it also in the chat. So if you go to the link there, you will be able to provide your vote. And so I promised I was going to be quick. So with this, I'm going to leave the podium to Landon, who is going to start announcing the students for the pitch presentations.
Awesome. Thanks, Marco. All right, first up, we have Andrew Atkinson. So I will share my screen. Hopefully everybody can see that. And when you're ready, Andrew, go ahead and take it away.
All right. Hi, all. You guys can all hear me okay, right? All right. Cool. Hi. My name is Andrew Atkinson, and my master's thesis was on structural optimization of composite laminates for automated fiber placement. So basically, automated fiber placement, or AFP, is what Boeing, Airbus, NASA, every large aerospace manufacturer uses to make massive carbon fiber and other composite laminate structures. And structural optimization is a design technique by which numerical modeling can be used to design the shape of these structures. And right now, the current state of the art in structural optimization does not take into account the unique manufacturing limitation or design limitations for AFP. And my thesis was implementing a constraint into the numerical optimization methodology such that the resulting ply structures can be manufactured using AFP. I think that was about the time that I had. So
Awesome. Thank you. For those interested, he will be in room number 1, so go check him out afterwards. And next up, I'd like to ask Akil Kyrie, please, or Kyrie, sorry.
You got it.
Please go ahead and whenever you're ready.
Cool. Thanks, Landon. So my name is Akil Kyrie. I'm a first-year PhD student in the plasmas focus, working with Professor Schumach. So no discussion of nuclear fusion is complete without an interesting but perhaps sometimes simplistic fact about the scale of what fusion energy would be, just to put things into perspective. So here's one that I like from a fusion text. So if you took all the deuterium, that is an isotope of hydrogen that exists in seawater and is the planned fusion fuel for reactors, if you took all the deuterium in the oceans and you powered fusion reactors under a standard steam cycle, that would power the world for about 2 billion years at 2007 consumption rates. So fusion energy, considered by many to be the energy source of the future. There are vast fuel reserves. It's carbon-free and it's relatively safe, far safer than the fission alternative. So this is the dream essentially, but it's been quite an elusive one for decades. Now there are many concepts for achieving fusion. The one I work on is known as the Z-pinch. It's compact, relatively simple compared to others, and that also makes it relatively well suited for propulsion for a spacecraft. But there are many challenges. Too many to cover now, but I'll cover one aspect of my poster session. Essentially, to get fusion, you need your field to be hot, so hot that it's a 100 million degree Kelvin plasma. And it turns out that at these temperatures, what do you know? Everything melts. Bottling up your plasma in a very multiple container is not an ideal situation. So we've come up with ways to get around this, like magnetic confinement. Since plasma is made up of charged particles, it's conductive, so we can manipulate it with magnetic fields and shape it and confine it. But you still need some solid vessel, and plasma still leaks out of your magnetic field lines, touches the walls or electrodes, and in some cases you need this. This results in a whole host of processes, and we call those plasma material interactions. So my research is about the interaction between our plasma and the solid electrodes on the Z-pinch and what happens in that interaction. Thank you.
Awesome. Thank you. Breakout room 2 afterwards. Next up, we have Arya Thayyer.
Can you all hear me?
Yep.
Right. Hello, my name is Arya Thayyer, as you just heard. I'm a first-year PhD student working with Owen Williams in Williams Lab. I've been studying the hydrodynamics of cross-flow turbines operated under advanced control strategies. So first off, you might be wondering, what is a cross-flow turbine and why should I care? Well, in the wind and water renewable energy field, there's 2 main designs. There are axial flow turbines, where the flow is parallel to the axes of rotation, such as the very large white turbines that you see in the plains of central Washington. Second, there are cross-flow turbines where the flow is perpendicular to the axis of rotation, such as this little example on my slide. Recent work in these has shown that in arrays, they can constructively interfere, resulting in higher power per unit area of land. Additionally, these turbines are insensitive to the flow direction, making them ideal for river and tidal application, where the flow direction shifts with the tides. And lastly, since the tides are caused by the moon, what's cooler than renewable moon power? Traditionally operated under rotating at a constant speed. we decided to look at sinusoidal variable velocity control. This is known as intracycle control, where the angular velocity of the blade varies sinusoidally about a mean velocity. By changing the control parameters, our amplitude and which is like how much, or the difference between our max velocity and our minimum velocity, and our phase shift, so where our maximum velocity is relative to our inflow direction, we found that we can change the performance and the forces on our turbine. The exciting thing about this intracycle control is that with no additional cost to the turbine, we can increase the efficiency by up to 15%. To understand why we see these improvements, we've captured the flow field near the turbine and just downstream. The resulting flow field that can be seen above, when captured under different control conditions, will provide insight into the beneficial hydrodynamic structures and will allow future optimization of these turbines. Thank you, and feel free to come check out my breakout room.
Awesome, thank you. Breakout room 3. Next up is Brian Lee.
Hello. Hi, my name is Brian Liggy. I'm a PhD student working on the RAM accelerator under Carl Nolan. So first, a RAM accelerator is a chemical propulsion device capable of accelerating projectiles or vehicles up to orbital velocities. It was originally developed here at the UW in the 1980s, and it gets its name from its propulsive cycle, which is a close analog of the ramjet engine, as seen in the upper image here. It has applications ranging from orbital launchers to military and defense, and even to things like drilling and boring. My immediate research goals revolve around bringing this longstanding technology to commercial industry for the first time. This has led to the necessary focus on the baffled and railed tube RAM accelerators, the BTRA and the RTRA, which accommodate the use of simpler and cheaper axisymmetric projectiles instead of the more complex projectiles, finned projectiles used in the original RAM accelerators. We've developed and tested new, more optimal BTRA and RTRA designs and validated a variety of propellant classes for use over a wide range of operating conditions. Additionally, my work has also included the development of 2 new patented technologies that will prove critical to commercial viability of RAM accelerator systems. First is a new RTRA configuration dubbed the RTRA with sweeper baffles, which features a highly efficient RTRA with periodically spaced baffles that allow the use of higher performance propellants with even higher efficiencies. This configuration is depicted in the lower left image. The second technology is called a baffled start stage, or BSS. The BSS, depicted in the lower right image, allows any RAM accelerator to operate without an obtuator, which is a Sabo-like device separate from the RAM vehicle that travels behind it and aids in the initiation or starting of the RAM accelerator. In most applications, having a second body, the obtuator, traveling down tube inhibits efficient and rapid operation, as the obtuator must be removed each time. The BSS features a short section of baffles filled with a carefully tuned propellant that is placed at the entrance of a RAM system and reliably starts the RAM accelerator without using an obtuator. For more information on this research, please attend my poster session. Thanks for your time.
Thank you very much. All right, next up we have Curtis Promislow.
Hi, can everyone hear me?
Yep.
Okay, so my name is Curtis Promislow. I'm a PhD student under Professor Justin Little in the Space Laboratory, and I research high pulse rate inductive pulse plasma thrusters. So let me start with sort of the problem that sort of motivates my research, and that is basically can be summed up by space is big. As Douglas Adams said in The Hitchhiker's Guide to the Galaxy, you won't believe how vastly, hugely, mind-bogglingly big it is. And to sort of illustrate this, I have this fun fact that you can actually fit all the planets in the solar system in between the Earth and the Moon, and we consider that pretty close. So there's a massive amount of space that you have to travel to get anywhere, and so that's sort of the challenge, is to cross that space. And so unfortunately, one of the sort of challenges involved in that is something known colloquially as the tyranny of the rocket equation. And basically what that says is, unfortunately, since you're carrying all your fuel with you, you have to carry a lot of it. And so you can sort of see this mass breakdown of a typical rocket, and usually it's somewhere between 80 and 90% fuel. And only, in this case, you're talking about a few percent worth of payload. So the challenge is to try to get more payload to your destination. And so one way we can do that, you still need conventional rockets to launch into orbit. But once you get up into space, you can use something called electric propulsion. And that is basically just a way to make the most of propellant once you get in space to try and maximize your payload. And so what I work on is what's called high pulse rate inductive pulse plasma thrusters. And basically, they sort of form this plasma from a propellant, and they make it really, really hot, and they accelerate it really, really fast. So here you can see in these diagrams here, in the top left corner, you have our plasma that we expect to be at around 11,000 degrees Kelvin, which is hotter than the surface of the sun. We have a nice high-speed camera that goes at 5 million frames per second. We use that to sort of investigate how this plasma is generated. In the bottom right, you can see we also use the same camera to track current sheet motion, the motion of the plasma, and we expect it to be around 22,000 miles per hour, so pretty fast. And then finally, we can also, with this unique type of thruster, we can investigate gas mixtures. And so here we have two types of gases making these pretty colors. And so if you'd like to learn more, please attend my poster session, which hopefully I will make, because I have some conflicting deadlines, but hopefully it'll work out.
Awesome. Thank you, Curtis. Next up, we have Eddie Ting.
Hi, can everyone hear me?
Yep.
Okay. Hi, my name is Huang Ting, and I go by Eddie. I'm a PhD student co-advised by Ellie and Moran. I work on two projects, which are wind tunnel aeroservo electricity and supersonic configuration at low speed, abbreviated as SCALES. I'll first talk about wind tunnel aeroservo electricity work. Aeroservo electricity is an interaction between structure and aerodynamics. Flight fuel can be saved by designing a lighter structure of the aircraft. However, the flexible airframe and the flow around the vehicle lead to aeroelastic problems, such as gust-low, ride comfort, and flutter. Incorporating active control suppressing such a phenomenon is called aeroservo electricity. The research group developed the flexible model to demonstrate flight control in the wind tunnel. My work focus on the gust liberation using prior knowledge, which assumes incoming gust is known by the realization of a LiDAR technology. And the preview control is tested to be more effective comparing to feedback only. And for the other project SCALES work, there are renewed interest in the supersonic airliners and business jet making trips from Seattle to Tokyo from a 10-hour flight to 5-hour or less. Most supersonic jets are optimized at cruise speed, but often neglecting low speed impact at takeoff, approach, and landing. We study on how the shapes and configurations affect handling quality, dynamics, stability, and control of the aircraft, which is tested at the Kirsten Wind Tunnel. My work focuses on the experimental data reduction and system identification of both linear and nonlinear behavior as a function of configuration shapes, control surface deflections, and flight conditions, and use the resulting models for control studies. And thank you.
Thanks, Eddie. Next up, we have Elliott Jennis.
Okay, thanks, Landon. So spaceflight is hard, but landing on Mars is harder. Just 40% of all missions ever sent to the Red Planet have actually succeeded. And most of these failures happen during a phase of flight called entry, descent, and landing, or EDL. And this term is used to describe the process that takes a vehicle moving at Mach 20 in the upper atmosphere to a soft touchdown on the planet's surface. Many of you may have seen the footage from the Mars 2020 landing last year. Their EDL procedure was incredibly complex, using supersonic parachutes, followed by retro rockets and the Sky Crane system, all required to land something that's basically just the size and weight of a Subaru Outback on the Martian surface. If we imagine sending something like the Apollo capsule to Mars, which is over 10 times that mass and pretty cramped for people at least, we can calculate that even with larger supersonic parachutes, it would crash into the ground at speeds close to Mach 2. And this is because Mars has barely 1% of the atmosphere that we enjoy here on Earth. So to address this problem, new EDL solutions are needed for human scale missions. And one possible solution that my research focuses on is supersonic retropropulsion, or SRP. This technology uses retro rockets to decelerate vehicles during the supersonic phase of EDL. Over the past 2 years, my lab group and I have been developing the testing capability to address a huge gap in research around SRP, and that is being able to approximate Martian relevant flight conditions in a wind tunnel, which is something that has never been done before for this application. 2 phases of work were undertaken, a construction and design phase where we created the facilities needed to collect this data, and then a testing phase where we collected a unique data set which served to validate non-dimensional parameters that we use to simulate Martian conditions. By varying temperature and gas composition in our wind tunnel, we could see if the chosen parameters capture the thermodynamic effects that we can see on the flow field. And our results, in fact, show a clear linear collapse of this data using our non-dimensional parameters, which is shown on my slide. Landon, if you want to press play, I think there's a video as well. Maybe not. Regardless, come visit my booth where I show cool videos of supersonic flow and cool pictures like this and talk more about how we did this and why it matters. Thank you.
Awesome. Thank you very much. Yes. Room number 7 for you. Sorry about that. Next up, we have James ONeil.
Thank you. So, hi, everybody. I'm a fourth year PhD student with working in UW LEMS with Professor Yang, and my research focuses on the crashworthiness of filament wound composite origami tubes. And the main motivation behind my research is that I want to improve on the crash performance of straight wall tubes, which are tubes that are like cylindrical or just like they're characterized by having a straight wall with no corrugations to their length. And these tubes are usually used as like crash boxes and like energy dissipation systems for vehicles such as cars, trains, and others along that same vein. And although these tubes are very effective at dissipating energy, they do tend to impart like large impulses on passengers or cargo that you're trying to protect. So these would be like large forces over a short period of time. And this can be detrimental to the safety of passengers. And so we propose, what I've been working on is proposing using the Cressler origami architecture, which you see here in the middle image. And this origami architecture under compression is characterized by having like a coupled axial and twisting motion, which is guided by its creases. And because of the full pattern of this origami, there are convex regions between the valley folds that are labeled on that image, and we can actually wrap around those convex regions. So I construct these tubes using carbon fibers, and I give them an epoxy resin matrix as well to stiffen them. And I evaluate their crashworthiness using a combination of quasi-static compression experiments as well as numerical modeling. And if you click the slide again, there should be a video that comes up. There we go. If you click it one more time, I guess, oh, maybe not. Okay, well, if the video, I guess, worked in this case.
Yeah, I think this is a case of Google to PowerPoint to SharePoint fail. Sorry.
No worries. If the video worked anyway, you'd see that this origami tube can actually maintain a stable collapse, which means that not only can it absorb a decent amount of energy, but it would improve the safety of the energy dissipation system. And the goal of my research is to design these tubes so that they either can absorb about the same amount of energy as a straight wall tube or more, and maintain the stable collapse mode, which would again improve the safety of the energy dissipation system. So if you want to learn more about that, please come visit my poster. Thank you.
Thanks, James. Go see the video at his breakout room. Next up, we have Jeremy Brockman.
Okay, well, everybody, my name is Jeremy Brockman. My research focuses on structural composites, which are used ubiquitously in aerospace, defense, and energy industries. Most notably, composites are used for primary structures on commercial aircraft, fighter jets, wind turbines, or rockets. Now, this prevalence occurs due to composites possessing superior strength to weight, corrosion resistance, fatigue, and energy absorption when compared to traditional metallics such as titanium, steel, and aluminum. But despite this prevalence in industry, the mechanisms in composites by which fracture initiates and cracks also propagate are just generally not well understood. And this is primarily due to the inherent complexity of composites and anisotropic behavior, and also in the many different damage mechanisms that composites possess. So it's kind of the duty of the academic community to develop more accurate, more reliable, and more efficient tools to analyze composite fracture. So in my research, I've designed and developed a novel and cost-efficient experimental technique, colloquially named the gap test. And this technique is for composites, and it investigates the fracture resistance under biaxial stress state. And just as a measure of utility, a biaxial stress state is the dominant stress state for a commercial aircraft or rocket fuselage, or any pressurized cylindrical aircraft. And then from this research, I showed for the first time in academic or professional literature that a composite's fracture resistance may be reduced under this biaxial stress state. This results in the structure being dangerously weaker than expected and reducing its factor of safety. I also coupled this experimental work with a computational effort, and I developed a finite element analysis framework that can replicate these experimental results. And then from this computational framework, this is going to obviate a need to undertake a large and expensive experimental effort, which is just not available to some researchers. And so instead, future studies may leverage the immense computational power that is available today. So further works can simulate experiments instead of execute them in the real world in a much more cost-efficient manner computationally. So my research and further efforts are of critical importance, as the engineering community at large will now be able to develop more accurate computational models and certification guidelines for structural composites. And then ultimately this will lead to safer structures and reduce potential loss of life for human-bearing structures like rockets, airplanes, or civil buildings. So thank you.
Thank you very much. Next up, we have Koshiro Yamaguchi.
Hey guys, can you hear me?
Yep.
All right. Hello everyone. This is Kosuke Yamaguchi. I'm a fourth year PhD student working with Professor Yang, and today I'd like to introduce my research about origami mechanical metamaterials. So origami is that originates from the art of paper folding, and now that origami technique is regarded as engineering application to make reconfigurable and transformable structures. So can you play the video? So as you can see on the left panel, if we manufacture origami structure, that structure can perform a lot of deformation, a lot of transformation, and it actually changes the mechanical properties as well. So first objective of my research is analyze and verify the design space of origami mechanical metamaterials. And after analysis and experimental verification, we discovered some of the unprecedented behavior in mechanical properties compared to the traditional material. So on right panel, the blue vector shows the traditional materials, like general behavior. So in the space of density and stiffness, a traditional material can occupy just one point on this plot. And it generally, there's a correlation between density and stiffness. But in origami mechanical metamaterial, there's a very unique behavior where density and stiffness has an inverse correlation, and one metamaterial can change the relationship between density and stiffness. So one material can move around this density and stiffness space. So for detail, I would like to introduce furthermore in my poster presentation. Thank you.
Thank you. Please visit breakout room number 10. Up next, we have Meng Yuan Wang.
Hi, can you hear me?
Yep.
Thank you. Hi, everyone. My name is Meng Yuan. I'm from the Ring Lab. My research topic is about the next generation of aviation. As you can see, excuse me, as you can see from the right top picture, there are a lot of issues with the conventional aircraft, such as pollution, noise, limited petroleum resources, etc. And the flight cost and maintaining cost are also very high. Most of these issues can be solved by electrically propelled aircraft. The electric aircraft, it's emission-free. The propulsion system is highly efficient, and it's also quiet and cheap. Besides, the projection of the battery development is very promising. So we believe that this will be the future of aviation. My research is twofold. On the aircraft level, I tackle this area from optimization perspective and focus on the energy management for electrically propelled aircraft. So I have designed a trajectory optimization algorithm for an all-electric aircraft to save the operating cost for different flight phases. For the hybrid electric aircraft, we have two power sources in the propulsion system. So we have developed a power allocation algorithm to optimally decide the power distribution between the engine and the electric motor. The current problem I'm working on can be addressed as to charge or not to charge. We want to identify flight conditions for two different hybrid structures to be fuel efficient if we want to charge the battery during flight. On the urban air mobility level, we focused on the network design problem through optimization. So the problem we have worked is how to select vertiport location and the scales in a metropolitan city in order to minimize the traffic congestion in a new hybrid ground air transportation network. That's it. Thank you.
Thank you very much. Next up, we have Purna Alango.
This might be another one that didn't show up like it's supposed to. So I apologize.
Yeah, there's a couple clicks on this one. but
Okay.
We'll get it. Purna, are you there? I can't hear you. Okay, perfect. There you are.
Thanks, Len. So imagine a scenario where a vehicle has to reach one of the multiple targets, but it does not have complete information about its surroundings. So it doesn't really know which target it can actually reach. So it's desirable to procrastinate and not make a decision on choosing a target and wait for more information to arrive and then make an informed decision. Can you press a few times there? A little bit more, and once more. Okay, so the DDT algorithm that we developed, which is deferred decision trajectory optimization, helps us do this precisely. It generates a series of branch points, one more click, which allows the vehicle to procrastinate, gain more information, and choose a target as more information gets available. Consider this example of a quad rotor. Can you press ahead? Yeah, consider this example of a quad rotor where it reaches the first decision point and realizes that actually, can you go back a little bit? I think there is a once more, one more.
Sorry, if there's something missing here, I'm not sure if it came through.
Oh, just one more. Okay, no worries. Can you just press once more?
Yeah, forward it. Sure.
Yeah, so consider the example of this quad rotor where after it reaches the first decision point, it realizes that first and the second targets are not reachable. So it can discard them and move on to the remaining 3 targets. And it can follow this sequence of branch points, and as it gains more information, it can make an informed decision and achieve some form of success in the mission. Next slide, please. A very practical application for this algorithm is planetary landing, where we may not have complete information about the landing sites a priori. Can you play the animation here? Oops. Looks like it didn't work. No worries. So the DDT algorithm can help us generate feasible landing sites without actually compromising the mission and allowing the vehicle to gain more information as it nears the landing sites. I'm happy to share more details in the breakout. Thank you.
Thank you very much. All right, next up we have Sarah Lee.
Hi, my name is Sarah, and I want to talk about what happens when autonomous technology takes over our lives. So according to stats, autonomous vehicles will make up about 10% of the total driving population by 2030. And this trend towards large-scale deployment of autonomy is also true in aerospace robotics in the form of drones and satellites. So in autonomy, the fundamental assumption is that the vehicles operate in a stationary environment by itself. And this is no longer true if autonomous vehicles are sharing airspace or road space. So to address this, my research focuses on how to modify existing autonomous algorithms so that they can safely and optimally coexist with each other. So my research applies game theory and optimization in 3 different directions. One is policy synthesis at scale. So in order to coexist, autonomous vehicles must plan around each other. We derived a distributed multi-agent algorithm where the total algorithm complexity grows linearly in the number of players. This improves on the exponential complexity of general multi-agent decision-making. The second idea is to incentivize preferred group behavior as a top-level system operator. To do this without knowing each player's private costs, I propose tolling each player's costs to naturally shift the group equilibrium. We apply this algorithm to a rideshare scenario using the 2019 taxi demand data for Manhattan and show that the congestion in Times Square and Wall Street can be reduced by using tolls as low as $1 per hour. The last direction focuses on autonomy in the presence of human-operated vehicles. The goal here is to make decisions when the player cost is uncertain, and I extended the popular dynamic programming Bellman operator to operate on sets of player costs. And these value function sets are then used to make decisions with worst-case guarantees. Finally, I'd like to thank my advisors and collaborators for their support in these projects. Thank you.
Thank you, Sarah. Next up is Scott Lee.
Yeah. Hello, everyone. My name is Shai-Feng Li. You can just call me Scott. I'm a PhD student under Professor J.K. Yang. My topic today is exploration of coral behaviors via coral motions. Coral is one of the most valuable species in the world and also support great diversity in the ocean. If you do the scuba diving in the ocean, you can see the beautiful corals with vivid colors. They're like rocks that cannot really move. And yes, corals are usually considered as immobile creatures. They cannot run or swim like other animals do. But on the coral surface, there are 3 noticeable parts that can move: tissues, polyps, and tentacles. So what is the function and significance of these motions? These motions are fundamental behavior trait of the coral, and they play an essential role in feeding, competition, reproduction, survival, and fitness. So besides, coral motions are the important features to study the coral behavior in response to the environmental conditions. So how do they move? Are the coral motions following any rules? This is the question I'm going to answer in my recent work. I use various experimental observation techniques and modeling methods to study the coral motion. I'm able to capture the subtle and imperceptible motion of coral tissues. I also find the correlated fractional browning motion of coral polyps. And I also find the tentacles are having the elliptical motion with a perturbation of 1/f noise. So from this study, I have gained the unprecedented understanding into coral behaviors in response to the changing environmental conditions. This will definitely help us to save corals in the situation of current global coral crisis and climate change. Yeah, if you want more information and details, you're welcome to see my poster. Thank you.
Thank you very much. Next up, we have Sean Fennessy.
All right. Hello, everyone. My name is Sean Fennessy. I'm a graduate student working with Professor Salviato. In my research, I'm modeling a computational model for composites, which find a nice application to designing the attritable aircraft. So if you push next. Yeah, and the composite material is one of the best choice material for designing these type of aircraft, thanks to the lightweight and also superior strength and and stiffness. So push next and next. Yeah, so what's novel about our approach is that we explicitly model the mesostructure of composite materials. As you see in this figure, we model the fibers as beams and matrix with the surrounding elements. If we put next. In this approach, we can capture the complex damage mechanisms such as transverse crack as shown here and next, and also the micro buckling of fibers. These are the inherent damages that occur due to the characteristics of mesostructure of composites. So next, yeah. So with our model, we envision to provide design guidance and the reduction in high cost experiments. And if you play the video, if possible. Oh, so I guess the video doesn't play. So through the material characterization and structural analysis on parts. So if you guys are interested to watch the cool animation of these simulation results, feel free to stop by the poster sessions. Yeah, thank you.
Thank you very much. Next up, we have Skye McKenzie.
Hey guys, can you hear me?
You're quite quiet.
How about now?
That's great.
Awesome. Hey guys, my name's Skye McKenzie, and I'm a graduate student working with Professor Bechet Ashikmashe in the Autonomous Controls Lab. And here I'm presenting a visual modeling system that enables users to seamlessly model constrained trajectory planning problems for autonomous aerial drones. So the intuitive GUI-based interface of our system enables the user to specify trajectory goals, add and remove motion constraints, and update parameters in real time. This interface acts as a high-level parser that converts graphically specified constraints into the proper mathematical form for the underlying sequential convex programming, or SCP, algorithms that our group develops. The trajectory solutions are generated within milliseconds using our custom solvers and displayed instantly for the user to transmit to the vehicle for tracking. And what's more, these trajectory solutions are desirable because they minimize fuel, adhere to vehicle dynamics, and satisfy all specified constraints. So SCP algorithms for trajectory planning are powerful due to their fast solution times and dynamic feasibility. But although such algorithms can run in real time after implementation, formulating new problems has historically taken subject matter experts hours, days, or even weeks. So our visual modeling system is a novel parsing interface that allows non-expert users to interact with the physics-based problems at a human level on relevant timescales by removing analytical steps. In this way, our work has unlocked the real-time potential of SCP path planning algorithms for all users in dynamic environments as constraints evolve. In addition, this system acts as a sandbox where researchers can gain intuition on generalized algorithm behavior and promises future directions of sensitivity analysis for output solutions as a function of input constraints. Our visual modeling system's been demonstrated on numerous indoor and outdoor flight experiments, and some example footage of these flights is available on our website. Thanks.
Awesome. Thank you very much, Skye. Up next, we have Spencer Cressler.
Hi, everyone. I'm Spencer. I'm a first-year PhD student with Meng Yuan. This past year, I've done an intensive look at distributed consensus algorithms on Lie groups. This is a fun and relatively unexplored topic in control theory. So consensus algorithms have a neat history that begins in biology with the study of how fireflies are able to sync their blinking patterns. And now this is used in nearly every field of engineering. So for instance, the power grid uses consensus algorithms to allocate resources. At a foundational level, consensus algorithms drive a group of agents to a single point in a distributed fashion. And usually this is done on vector space, but I have found that there's motivation to generalize this to Lie groups. So Lie groups are highly symmetric manifolds that appear everywhere in physics and engineering. So for example, the state space of every mechanical system, like a robot arm or a car, is a Lie group. Now, in a control theory, when your system isn't a vector space, like a robot arm, you'll often linearize your system and then just apply ordinary linear systems theory to it. However, linearization has its limits. You can only stray so far from the origin before your linearized dynamics lose their meaning. So for instance, with attitude control of a satellite, if you want to rotate the satellite 180 degrees, you will need something stronger than linearized dynamics. Now, I found that many concepts and techniques from control theory naturally generalize to Lie groups. Like vector spaces, Lie groups have very nice properties. They're computer friendly, and overall, they're a lot of fun to work with. So as a result, linearization isn't always necessary when you're dealing with certain dynamics on Lie group state spaces, usually ones with lots of symmetry. So I'm particularly focusing on how to generalize consensus algorithms, which have predominantly been studied on vector spaces to Lie group state spaces. And I'm currently working on a project with JPL using some of these techniques for estimating the attitude of space debris using like a distributed network of satellites with cameras. So please see my poster session if you want to learn more. Thank you.
Great, thank you. Up next, we have Taiwan Kim.
Can you hear me?
Yes.
Yeah, I'm Taiwan. I'm working on the initialization problem of trajectory optimization algorithm. And the initial trajectory is a key input of many of trajectory optimization algorithm. So in the left figure, the green dashed line represents the initial trajectory. So many trajectory optimization algorithms starting from the initial trajectory then updates its trajectory to the black line, which is the local optimal solutions. So you can easily imagine that if the green line is close to the black lines, we can see that the trajectory optimization algorithm converges quickly. So our idea is to train neural net policy that can receive the state and generate the counter input. With that policy, we can generate many trajectories from different initial positions. So our idea is to borrow the idea of the SCP. So we update the neural net policy with every iteration of the SCP. So the right figure is the result of the application of the 6DOF power descent guidance. All the trajectories in the videos are coming from the neural network. And we found that with the trained neural net, we can generate safe, local suboptimal solutions. And with that trajectory generated by neural network, the trajectory optimization algorithm converges more quickly. Yeah, if you're interested more, please join it. Thank you.
Thank you very much. Up next, we have Tyler Munt.
Hi, can you hear me?
A bit quiet.
About now?
It's a little bit better. I think it'll do. Yes, that's great.
All right, cool. Hi, my name is Tyler Munt, and I'm a PhD candidate under Dr. Nolan. My research concerns geometric scaling of cylindrical rotating detonation rocket engine combustors. In a rotating detonation engine, or an RDE, as we use for an acronym, combustion is accomplished by detonation waves that travel circumferentially around an annular channel. This approach stems from intensifying the tangential acoustic instability that caused catastrophic damage in early rocket engine combustors. Due to the use of detonation waves, an RDE is considered a pressure gain combustor, which theoretically exhibits a total pressure gain rather than the loss we see in traditional deflagration-based combustors. If realized, this would lead to a reduction in the size, weight, and complexity of supporting hardware, as well as provide efficiency advantages. This technology also has applications in stationary power generation and air-breathing propulsion. The latter of these two has seen a few headlines lately, as the AFRL has awarded a contract to Pratt & Whitney to produce a ground demonstrator model. Even though the first in-space demonstration RDE was achieved atop a Japanese-sounding rocket in 2021, the theoretical benefits of an RDE have not been realized, and the fundamentals of design and performance are not well understood, according to a 2018 paper also from AFRL. As such, an experiment-driven effort was proposed to obtain scaling laws and investigate small-scale RDRE dynamics and operability with an eye toward satellite propulsion applications. Two studies, each varying only a single dimension of the combustor, were planned. The first varied the radius of curvature by adjusting the outer diameter, while the second varied the annular gap width at the smallest diameter scale of the first study. Injector mixing characteristics were held constant, as were propellant feed conditions, and then those were scaled by mass flux when needed. In the end, 3 modular engines were designed, fabricated, and tested, with 6 configurations used among them, 1 shared by the 2 studies. A total of 407 successful runs were recorded, and currently the data is being analyzed for trends and constants, with correlations to geometric ratios and detonation cell size planned.
Awesome. Thank you very much, Tyler. Lastly, but not least, we have Yoshihiro Miyazawa.
All right. Oh, it seems like everything is playing.
Yeah, I could get it playing
it's
for
all right.
sure.
Okay. So I assume everyone can hear me. And so what I really want to do here is to collect the energy. So if you click one more time on the very left top corner, usually we can, if we have a lump of energy considered at a certain location of the material, it disperses into the space. But under certain condition, if we click one more time, we can see this wave focus is really high without applying any external force. So we don't have to work actively on the material in order to collect this energy. It's completely passive. And this kind of a phenomenon is called wave focusing, which we can often see in the water wave, like on the right panel video, where we already saw very high peak focuses at the center after a while. Right. And this is what we want to do, not in the water tank, but instead in the structures, which leads us to the very bottom video, where we see the very high energy concentrates at the center of the origami lens that we are using. And this is just a numerical prediction of it, but our next step that we are considering is to, of course, experimentally see this wave focusing in the mechanical system. And if you want to know a bit more detail about it, please feel free to join the pulse session.
Awesome. Thank you very much. There we go. All right, here is the list of all the rooms. I guess breakout room time.
Yes. So Marco, if you'd like to honor our judges, reveal their identities.
Yes. So welcome back, everyone. I hope you enjoyed the presentation as much as I did. I was overwhelmed by all the students' work. So yeah, thanks a lot for that. And so, as I promised, now I'm going to reveal the judges. They have already made their verdict. So, and Christy is going to announce the winner very, very soon. But before that, let me just acknowledge the contribution of our judges. So we had Dr. Roger Myers from Aerojet Rocketdyne, Francesco Di Leo from TerraPower, Chris Bosetti from Boeing, and our Rising Star faculty, Amir Tagvei. So thanks, judges, for participating. I hope you had fun as we did. And without further ado, Christy, I am going to hand it to you.
Awesome. Thank you. Well, this was great. I want to add my thanks to everybody who helped organize this. Full disclosure, I actually had nothing to do with organizing this other than agreeing to put department money in for the prizes. So that is awesome. That's an outcome of some of the strategic planning we've been doing in the department. Okay, so I'll start with our third prize winner. Everyone did awesome. So really proud of everybody. Third place goes to Spencer Cressler, distributed consensus algorithms. Sorry, what?
Oh, yay.
Congratulations.
Yay.
How do you pronounce your last name?
Like the car, Chrysler.
Okay, Chrysler. Distributed consensus algorithms for Lie groups was the title of yours. Second place goes to Elliott Jennis, thermodynamic scaling of supersonic retropropulsion flow fields. Wherever you are here, congratulations. We can't fit everybody on one screen, which is awesome. And then our first place goes to Skye McKenzie. And I know I just mangled your last name. I apologize for that. Visual modeling system for optimization-based real-time trajectory planning for autonomous aerial drones. Awesome. Somewhere you're in here somewhere.
Wow.
There you are. Found you.
I did not expect that. Thank you so much.
Nice work. Okay, and then the People's Choice, which was fun to watch all the votes come in. It goes to Sean Fennessy, discrete mesoscale modeling of composites for attritable aircraft. Where is he? Somewhere on the screen. There we go. We should have renamed your.
Thank you.
Pop to the top. Cool. All right. We will figure out how to get your prizes to you tomorrow. Great work.
Yeah, thanks everyone for joining. It was a lot of fun. You made my day. Definitely, I was overwhelmed to see this participation, and we're gonna do it again next year.
You all did great. All of you did really good, and your research is really interesting. So thank you for sharing it today. It was really fun.
Thank you.
And I'll just put a plug in now for the ending part of Shark Week, which is Capstone Film Festival on Friday, which is always fun. So 4 o'clock Friday.
All right. Good night,
Take care,
everybody.
everybody.
Bye, everybody.
Bye-bye.